Hello physics students, this is Dr. Brinzy here, and this is a review of lesson 2.1.5, problem number 4. A lot of people struggled with this problem. So to give you an idea about how to do this, I am going to change some of these numbers up a little bit so that when I do it, you can do it for the numbers that are actually in the problem and be successful. So let's change this incline to a nice, warm, comfortable 45 degrees. So 45. All right, so let's make that 45. And let's say the river was 20 meters wide. And let's say the far bank is 10 meters lower, and then let's say the riverbank is 50 meters below the ramp. Okay, so alright, so we'll make all those changes. It's going to be a very similar problem to what you're actually going to do, but I'm just changing up some numbers here. Alright, so there are two ways to attack this problem. I'm going to show you the algebraic way first. That's probably what you're more used to seeing. But there's also another way that we can attack this problem that we stumbled across actually during tutoring the other day. And I thought it was such an interesting idea that I thought I'd pass it along to you. So let's get started with the traditional algebraic way. So let me see here. Let's get up a whiteboard here and thankfully all these little marks stayed up, so let's make a note of all those things, that we have an incline right here and it is 45 degrees, and then we have, let's see if I remember right, to see 20 meters to the other bank, and then the other bank is a distance of 10 meters lower than the top of the ramp. And let's extend that ramp a little bit. Okay. And what we have to find is we have to find the magnitude of his initial velocity that will get him across the bank. And just get him across the bank so that he barely makes it over to the other side without crashing into this nasty river ravine below. Alright, so now that I have all that information down, let's go ahead and erase these because we'll need that space later on. Alright, so let's draw, or let's make our XY table. So let's put this into X and Y components, X and Y. And since this is a problem that's asking us about that's mainly talking about displacement, let's go ahead and write down the displacement equations in each direction. So we have displacement in the x direction equals its initial displacement plus its initial velocity in the x direction times time plus 1/2 at squared. And we're going to do the same thing in the y direction. There we go. Okay. Now let's start filling in some numbers here. So my initial displacement in the x direction, we're going to say that that is equal to 0. So we'll set d equal to 0. Let's see, plus the initial velocity in the x direction. It's not this initial velocity up here at the top right that I need to figure out. It's actually, this Vix is the x component of this vector. So I need to actually break this down into x components, x component, and y component. So let's go ahead and do that very quickly. So let's see, let's draw a quick triangle. And if that's 45 degrees, and this is some value vi, then we know from SOHCAHTOA that sine is equal to opposite over hypotenuse. So the opposite has to be sine times hypotenuse, or hypotenuse times sine. So let's put VI sine 45 degrees. Okay, and we can end up simplifying that to VI times root 2 over 2. Okay, and the initial velocity in the x direction, well, the ka part of SOHCAHTOA says that cosine equals adjacent over hypotenuse. So the adjacent side I can get by multiplying cosine times the hypotenuse. So this x component will be v sub I cosine of 45 degrees. And that value is also root 2 over 2. Okay. So now we have our x component, which is this value right here. Let's go ahead and plug that in for our initial velocity in the x direction. So we have root 2 over 2 VIX. Oh, no, not VIX. This is VI now, right? Times t. Plus, let's see here, 1/2 AT squared. What is the acceleration in the x direction? Hopefully you just told me 0, because gravity does not work in the horizontal direction. So we're going to change that to 0. And what we are left with is just d equals root 2 over 2 v sub I times t. All right, now I have something here with 3 different variables, so let's see what additional information I can plug into here, either for d, for v sub I, and for t. I don't know what the initial velocity is. As a matter of fact, that's what I'm being asked to find. So I know I need to keep that a variable. I didn't get any information from the problem about t, the amount of time it takes to go a certain distance. So let's look at d here. So d, let's see, the distance it takes to cross the ravine is 20 meters, right? So I could set this distance equal to 20 meters. Okay, it's a little bit backward from what we're used to doing, but we can do it nonetheless. So let's set 20 equal to root 2 over 2 v sub I t. Okay, and for now I think that's about as much as we can do with that side. So let's go ahead and start thinking about the y displacement. So the y displacement, we can write that as d equals, we're going to say that we're starting off with a displacement of 0, so I'll write 0 there. Plus, now I have to have my v sub I in the y direction, which would be this component right here. So that is root 2 over 2 times v sub I times t. And let's see here, acceleration in the y direction, what is that? Hopefully you just said that's the acceleration due to gravity, which is negative 9.8. And when we multiply negative 9.8 times 1/2, what do we get? Hopefully you told me right away that is negative 4.9. So we get negative 4.9, or minus 4.9 t squared. Okay. Now, let's see here. I know I'm not given anything about velocity, initial velocity, that's what I'm trying to find. I wasn't given anything about time, but I was given some information about distance. Not only was I given information about distance in the x direction, like how far it has to go, but it also tells me that our daredevil professor is going to land 10 meters below the top of this ramp. So, what should I plug in for d right here? Well, we should plug in negative 10. So I have negative 10 equals, let's go ahead and skip the 0 because it doesn't add anything to our sum on the right-hand side. Root 2 over 2 v sub I times t minus 4.9 t squared. All right. Well, it looks like I have a system of equations here. Two variables, v sub I and t, and I have two different equations. This looks like a system of equations. So, I think I'm going to manipulate this one over here. Okay, and the reason I'm going to do that is because it certainly is a lot easier. And I think I could just go ahead and manipulate this to solve for t, because in the end I want to find v sub I. So I want an equation over here that only has v sub i's in it. So let's go ahead and do that. So let's get v sub I by itself. So I have to take and multiply both sides. Let's rewrite this v sub I t so it's clear what we have to multiply by. So I have to multiply by the inverse of this coefficient right here. And I know that the coefficient, excuse me, I know that if I multiply this by root 2, that I'm going to get 2 over 2, which equals 1. So let's multiply this side by root 2. And I want t by itself, so excuse me, I need to divide by v sub I. Divide by v sub I. So I have an expression that says 20 times root 2 over v sub I equals, let's see, those divide out. These two things multiply to equal 1, so I'm left with t on the right-hand side of this equation. All right. Now, I'm going to plug that t into everywhere. Oops. Let's snake that around like this. Everywhere that I see t in this equation over here, I'm going to replace it with this expression down here. So let's get started with that fun. Negative 10 equals root 2 over 2 v sub I times, now I've come across a t, so I have to replace it with this expression right here. So let's make a parentheses, 20 root 2 over v sub I, okay, excuse me, and minus 4.9, and now I see a t squared, so I have to replace the t with this expression right here. So let's make a set of parentheses, and since I have to square the t, I better square whatever value I replace t with. And let's put 20 root 2 over v sub I. All right. Now, let's do a little simplifying. I know that if I take root 2 over 2 and multiply it times root 2, I am going to get 2 over 2, which is equal to 1. So in a sense, these things multiply and divide out. Actually, let me put that in a different color. Okay. These three things, when you multiply and divide them, they equal 1. I also notice that the v sub i's divide out in this particular term. So I'm left with negative 10 equals, the only term I have left here is this 20. So let's bring that down. 20 minus 4.9, and then now I have to multiply all this out. Well, 20 squared is equal to 400. And root 2 squared is 2. And then v sub I, and let's make sure that we square that. All right. So this is an equation that you can simplify and solve for v sub I. Now, if you might not be as used to dealing with v sub the variable in the denominator. So let's go ahead and continue this just a little bit more, but you could probably skip ahead to the other way that I'm going to solve this, if you feel like you can solve this problem. So let's subtract 20 from both sides. So I have negative 30 equals negative 4.9 times, and then 400 times 2 is 800, so I'm just going to keep that up there, divided by v sub I squared. Alright, now let's make a little dirt here, and bring this up to right here, underneath. So now I have, let's see, I'm going to multiply. I'm going to multiply both of these sides of this equation by v sub I squared to get that out of the denominator. And let's remember that we're multiplying here. So these terms divide out. And now I have negative 30 times v sub I squared equals negative 4.9 times 800. And now I can just divide by negative 30. All right. And I get a value for v sub I squared. Now I got to do some number crunching. Looks like it's going to be something around 133, but I could be wrong. So 4.9 times 800 divided by 30. 130.6 repeating. All right, so 131 actually. So that's 131. And take square root of that, and v sub I equals, I get 11.4. Okay, 11.4, and I think our significant figures have us putting it in 2 sig figs, so we would actually report that it is 11 meters per second. All right. Okay, so our little daredevil professor, if he flew off this ramp at 11 meters per second, he would just make it over to the other side. All right, so now you have an idea of how to do problem number, I think it's 4 for the advanced physics and 5 for the AP physics. But I did promise that I would show you a different way to do this, so let's try a different way. All right, so I need all my details from the previous. All right, so I have 45 degrees, I have 20 meters, and we land 10 meters below the ramp. Okay. All right, now this might be an interesting way to solve this. Now, I'm actually going to try to solve these by drawing 2 different velocity graphs. So again, I'm going to split this into the x and y direction. And let's remind ourselves we had 45-degree ramp. Okay. And this v sub I is what we're looking for. And we had to go a distance of 20 meters in x. Oops. And we were going to land 10 meters below the top of the ramp. All right, and that's in a sense our final displacement. Okay, so let's draw a couple of velocity versus time graphs, because we have different velocity for x direction than for y. So this is time, this is velocity. Now in the x direction we don't have any acceleration. So what would we expect a velocity versus time graph to look like here? Hopefully you just told me that it is a horizontal line, which would be correct. And I'm going to go ahead and just remind myself that, hey, we split this up into 2 components, and the x component was root 2 over 2 v sub I. Okay, so we would have a horizontal line for the velocity in the x direction, and it is at a constant value of root 2 over 2 v sub I. All right. Now in the y direction, we have, actually, we have velocity in the y direction, and we're going to plot that versus time. Now in the y direction, our velocity is going to start off at whatever this y component is of the velocity, and that, since it's 45 degrees, it's also root 2 over 2 v sub I. So we're going to initially start with a positive velocity of root 2 over 2 v sub I. All right. And we know that since the acceleration is in the negative direction, we know that this line is going to have a negative slope. And that slope of this line, is what? That's our acceleration. And our acceleration is what? Negative 9.8 meters per second squared. So that is our slope. Well, goodness gracious, maybe we can actually, Well, I was going to say we could actually write the equation of this line if we wanted to, but I was just thinking about this, since we're all talking about displacement, it probably doesn't pay for us to actually draw that or write that equation. All right, so now what do I know about the final displacement in the x direction and the final displacement in the y direction? I know that I want to finish up 20 meters in the x direction from where I started. Okay, so at some time t final, how do we find distance when we have a velocity versus time graph? Well, we have to find the area under the curve, right? So at some t final, the area under this curve has to give us 20 meters, okay? That's what we want. And at some final time here, we call it t sub final, this area minus this area has to give me, negative 10 meters. You said, why negative 10? Well, because we are going to finish 10 meters below where we started, okay? So another way of saying that is that this blue area has to have an area of 10 meters more than this area here. All right. So where do we go from here? Well, I know that this times my time equals 20 meters. So I could write root 2 over 2 v sub I times my final time, t sub f, equals 20. Okay? And I could then use that as an expression to find my final time, t sub f, equals, it looks like 20 times root 2 or divided by v sub I. Okay? So I could plug that in over here. All right, and you're saying, well, wait a minute, this doesn't look too helpful yet. Well, you might be right, but let's keep on going forward anyway. Because you never know. Sometimes ideas are good, and sometimes they turn out really crazy. And maybe this is just a crazy idea of mine, and I'll be recording for nothing. But I'm going to keep on going, because it would be awesome if this really does turn out. I think it will. Okay, so I need to figure out what this area is for this red triangle. Okay? And I know that this is 0 when, let's see here. I need to figure out what this area is, right? Which means I need to figure out what this time is here. Like, how long did it take to actually get to its highest point? Okay. So I know that, let's go ahead and write this equation out. We can write the equation for the slope of this line, right? And then set it equal to 0, so let's go ahead and do that. So v sub y equals negative 9.8 times t plus its y-intercept, which is this thing right here, root 2 over 2 v sub I. Okay, and then I want to find the time when the velocity is what? 0. So I'm going to set this equal to 0. And it turns out I can add 9.8t to both sides. Well, this might just involve just as much algebra as the other one. And let's see here. I know that if I multiply both sides times the square root of 2, that this thing times the square root of 2 will give me 1. So now I have 9.8 square root of 2 times t equals v sub I. All right. And that means that this time that it took equals v sub I over 9.8 times the square root of 2. And you might be thinking, oh god, that looks terrible. And I think it's looking so terrible and ragged because I have lots of variables involved with this. But if I just had numbers, I think this would be looking a lot better and a lot more elegant. Just like we discovered the other day. It will work, but it just seems to be more clunky than the other method. So I think I'm going to abandon it at this point. But here's what I would do next. I would use this expression, plug it into here for my base, and then base times height. 1/2 base times height gives me this area. And then I just have to find what this time has to be. And to tell you the truth, I'd have to find this velocity too, which, oh man, this is getting even clunkier. To find out what time would make this area equal to negative 17, so that the total area of the two is negative 10. Yeah, this is a really clunky method. All right, so it doesn't work so well for this. It works great for other problems. So anyway, I'm sorry that you had to keep watching this, and I'll probably just make a note on the video notes to tell you to stop watching after the algebraic equation is finished. All right. Well, that didn't work as elegantly as I thought, but it would technically work. And anyway, good luck, and I look forward to seeing you soon. Bye.